In this video we're going to look at tree diagrams, but in this case we're going to have probability values in the tree diagram also. We're going to introduce this using an example. Suppose we have 3 boxes and each of the boxes contain black and white marbles. The number or the percentage of white marbles in box A is 3/5. The percentage of white in B is 2/5, and in C is 1/5. Now for the experiment we're going to choose a box randomly, and then from that box we're going to choose a marble. We're going to answer these probability questions. What is the probability of choosing a white marble? Also, what is the probability of choosing a black marble? And then finally, given we chose a white marble, what's the probability it came from box C? Alright, so looking at this tree diagram over here, remember we have a starting point, and then the first part of the experiment we choose one of the boxes. So we're going to choose A, B, or C. Now since we're choosing those randomly, they each have a probability of 1/3 of being chosen. So we're going to put that probability on the line, 1/3, 1/3, and 1/3, going to each of those boxes, A, B, C. Now if we've chosen box A, the probability that we will choose a white from A is 3/5. Therefore choosing a black from A will be 2/5. And we do that for each of the boxes. So for B it's 2/5 for white and 3/5 for black. Then C will be 1/5 for white and 3/5 for black. It's a little hard to see here. That's a 3 and that's a 2. So what are the probabilities shown in this diagram? Well, we have those individual probabilities, but also if we follow from our starting point out to an ending point, then that'll be the probability of choosing the box A and the box or a white marble. So if we multiply those probabilities through there, then that will give us a probability of A and white. If we follow through to the black marble, then that'll be probability of A and black. A and black. Alright, so we can do that for all of those. Now the probability of choosing a white marble will just be the probability of choosing A and a white marble plus the probability of choosing B and a white marble plus the probability of choosing C and a white marble. Now I said that each of those were the multiplication of those probabilities getting to that end point, so we're just going to multiply those values and then add them up. So we already did A and white. This is the multiplication of those two. B and white, we're going to do 1/3 and 3/5, and then, that's 2/5. I guess I mixed it up earlier. That's 2/5 and that's 3/5. So B and white is 1/3 and 2/5, and C and white is 1/3 and 1/5. Okay, so after we sum all those up, that'll give us a total of 2/5 for the probability of choosing a white marble. Now finishing up the problem on the back on this next page, we've got the probability of black. We just do the same thing. Probability of A in black, probability of B in black, and probability of C in black. Multiply those probabilities, 1/3 and 2/5, 1/3 and 3/5, 1/3 and 4/5, and then add them up, we get 3/5. Now the conditional probability that the marble came from box C, given that it was a white marble that we chose, is equal to probability of C and white, or C intersect white, over probability of white. Again, the W here matches with the W here. We already found the probability of picking a white marble. That was what we had on the previous page. It was 2/5, and the probability of C and white is just the multiplication of those two to get to the white marble, 1/3 and 1/5. And after we multiply those through and simplify, we get 1/6. Now let's finish up with looking at one more example. This one is going to be pretty much the same but let's look at how it might be worded. Where we have 3 workers in a factory that make parts, so they're making parts, and there's only 3 of them, and these 3 make all the parts that are made in the factory. So there's 25% are made by worker 1, 35% made by worker 2, and 40% made by worker 3. And that should add up to 100%. Now, of the parts that are made by each of the worker, the percent defective made by worker 1, so in other words, when worker 1 makes a part, 5% of his will be defective. When worker 2 makes parts, 10% of his will be defective, and worker 3, 15% of his will be defective. Now I made up this problem, but you can see I made it up so that the guy that's working faster, getting more parts done, has more defects. Alright, so the questions that we want to answer are, what is the probability of a part being defective? So any given part that the factory makes, what's the probability that it'll be defective? And then also, suppose we find that a part was defective, what's the probability that worker 3 made that part? Alright, we're going to use our tree diagram to solve this problem. Now I have to solve it on the next page, so let's take a look at the tree diagram. Tree diagram, we have all the workers, worker 1, worker 2, and worker 3, and 25% made by worker 1, 35% by worker 2, 40% by worker 3. And then of each of those, there's defective and non-defective parts. So worker 1 makes 5% defective, therefore 95% are not defective, and so on. 10% in 90, 15% in 85. Alright, so the 2 questions we want to answer are, what's the probability of any given part being defective? That'll be equal to the addition of the worker 1 in defective, plus worker 2 in defective, and worker 3 in defective. And we get those again by just following through to the end and multiplying those probabilities. So 0.25 and 0.05, 0.35 and 0.1, and 0.4 and 0.15. And we end up with 0.1075. Alright, now let's before we go on, let's see if that makes sense. 0.105. It's always good to look to see if that makes sense. Now let's look at just the probabilities of getting defective parts for each person. We have 5% for worker 1, that's the minimum that a worker has defective, and the maximum that a worker has defective is 0.15. So you could actually ask yourself, would it be possible for us to have less than 5% defective parts from this factory? And of course the answer is no. I mean, all of our workers are making at least 5% defective parts, so we know that that's a minimum that we could have for defective, and the maximum we could have would be 15% defective. So it's going to be somewhere in between there. And notice that that worker 3 makes most of the parts, so we might be closer to this value than this value, and we are 0.1075, a little bit closer than we are to 0.05. Alright, so let's also now calculate the probability, given that we have a defective part, what's the probability it came from worker 3? So we know that that'll be equal to the probability that worker 3 made it and it was defective, divided by the probability it was defective. We already calculated probability of defective, that was our 0.1075. The probability of worker 3 and defective is just the multiplication of 0.4 and 0.15 to get out to this spot. And so we multiply those two on top, and we get 0.5581, which is about 56%. So if we know if a part was defective, the probability it came from worker 3 is 55%. Now we can also look at this and see if it makes sense. If we just look at the percentages that each of the workers are making parts, any given part, we could say that what's the probability it came from worker 3? The probability would be 0.4, or 40%. Now if we look at the percentage of defectives, worker 3 is making the most defective parts. And so if we know a part is defective, then that tells us that it's more likely that worker 3 made that part than any of the other workers, because he's making the most parts and he's making the most effective parts. And so we see that by this calculation that, given that we know that it's a defective part, it's actually more likely that it came from worker 3 than if we just picked a random part and said what's the probability it came from worker 3. So that also makes sense. So it's the percentage, because he has a higher percentage of defective parts, actually makes this probability a higher probability.